Enjoying ourselves? Yes. Yeah, I'll put a stop to that, okay? All clear?
Yes, only one out next going back.
Fine, okay, thank you. Okay, members, our next topic is slot and ZL special antenna. Our speaker started at Sydney University doing electrical engineering, obtained his radio licence in 1972 and pursued a career in electronics. At his home in Willoughby, he built a 6-metre Yagi and a 23 centimetre phased array. He's had experience with marine radio and is currently involved with system software. At 23 centimetres, Yagi elements are very short and fiddly. And this is where a slot antenna is useful. On VHF frequencies, the skeleton slot works well with a broad pattern. Members, please welcome VK2ZIW, Alan Beard.
Yeah, good morning. Good morning all. Can you hear my voice? Yep. Sounds good? Okay. I've just showing you there what you can do with the slot with antenna and having all sorts of different shapes. So you don't have to always have that one shape. And as for other antenna purposes, I had to build a reference antenna that had a broad frequency response. So I built what's called a Vivaldi antenna. So that's an exponential curve feeding to a feed point. Right, so that's my little antenna that hopefully is broad enough bandwidth to test antennas like my slot that we've got here. I'll show you so that slot, and the reason I've tapered it in that sort of way is to give it broader bandwidth. Have I succeeded? Well, actually, not really. So let's have a look at its performance curve. Okay, so there's its performance. So there's its performance curve. So you can see that the SWR, or actually its what is it? Its return loss measurement is that blue line in that there curve. And you'll see that goes down very markedly at around about 1250 megahertz. So that's actually much lower than I really wanted it. I really wanted it near 1300 megahertz. But it's surprising just how much when you move things around that things change. So my original setup, I probably didn't use the particular pieces of coax that I'm using here. And even amongst my own bits and pieces I brought along there, you've got to be very careful at 2300 megahertz with your, not so much the type of coax, it's how the connectors and all that are terminated and whether they've got a right angle connector or whether they're a straight through connector. So it's at 23, you know, down at 70 centimetres it doesn't matter much whether you've got a right angle connector or a straight one, but up here it really does. Okay, so that's my attempt there in the slot antenna. Now, I had
Is that a capture or is that actual real time?
Well, I can scan it real time and put it into this continuous scan, but you can see with that you can adjust things, you know, move things around to see if the picture changes. And it's all over the place because there's reflections and everything here. This is not a very good antenna range, as you can imagine. Right, okay. So I did
what
test.
happens when you change the orientation?
Well,
Not a lot. Oh, it's getting better. Oh, because it's in the same plane. more or less.
Now you can see that this red line here is much lower. So obviously vertical polarisation is not this antenna's optimum,
Right.
which is exactly how it was designed to be in actual fact. And you can see there now that the optimum radiation from the antenna seems to be around about the 1290 mark, which is actually where I was planning on. Okay.
So you're actually measuring the signal strength from that antenna to that?
Yep.
Oh,
Yeah.
right, okay.
Yep.
So that should be a throughput.
And the blue line on our curve here is the SWR plot looking at that antenna.
How are you feeding the antenna? I noticed that it almost looks like at both ends are soldered. Is
Right.
the braid on one side and the inner on the other?
Yes, but I'm using a short piece of coax here as a capacitor.
Oh, the stuff.
Okay, so effectively, yeah, where the feed comes in here, soldered permanently there, and then goes across to the other side where I've got a short piece of coax. And of course, I had it out to here originally, and I cut it off with side cutters till I get the best SWR.
Right. Okay. So
Right.
so
Now, remembering at 23 centimetres, a small amount of capacitance between the copper plate, pieces of copper here, and the plate here is plenty enough to make good electrical connection, right? Because if that might be 5 PF in there, but 5 PF at 2300 megs, or sorry, 1200, probably 1 or 2 ohms of impedance, next to nothing. So that's all you need. So, because obviously you can't solder to aluminium, so that made it my easy way to connect to it. All right. Okay.
and different materials exhibit different properties.
Yeah. Well, the other thing too with the slot is the slot radiates obviously out the front and out the back. So you can put a cavity at the back of the slot, but that really knocks your bandwidth right down because the cavity is a resonant circuit, right? So I chose to just put a reflector behind and bend those to try and maybe if some of the radiation goes around there and comes out the sides, I'll be happy. Yes.
Are you forming a resonant cavity in a small sense by sizing the reflector the way you have?
Quite probably. This was just done empirically, as it were.
Suck it and see.
Yeah, exactly. Right, yeah. Okay. On slot antennas, you can also go over and do, you've probably heard of skeleton slot antennas? Okay, so this is I lashed this up yesterday in about an hour. I had some aluminium angle. Now, one of the things that's very important when you're doing a slot or any of these types of antennas, notice where the coax cable comes out here, down the centre. That's because if you put your finger on the antennas here and there, or here and here, you find that it varies the SWR quite a lot. So those are the hot areas of the antenna, the edges here and up there, right? So you've got to bring your coax cable out as close to the centre as you can, away from where it's hot with RF, right? So the same thing goes with your skeleton slot. You take your coax away at the centre point of your slot, because you think of this, there's a bit of a resonant circuit up around there to about there, and then down here around and back up to there. And we match it by connecting across there and feeding it in about the middle. And one of the other reasons I've used angle here is you can hide your coax cable inside the angle. It would be perhaps better if you had a U section, but I don't think it matters terribly much. You're just trying to keep your cable here from not introducing any magnetic effects from the cable as best you can.
What are the alligator clips doing?
The alligator clips, well, you match the SWR of the antenna by adjusting the unit up and down. Right?
Good question.
Right? Okay, and those other alligator clips are spares in case I lost one.
They're mechanical. Yeah.
That's right.
And then he used to say there's no such thing as a silly question.
Absolutely.
So you can have a play with that later on if you want to and look at the analyzer and see what it looks like. So
So that piece of metal in the middle is not connected to the feed line at all, is it? I can't.
yeah.
Oh, it is, right.
There's
okay.
a couple of lugs that I've
right.
screwed on there
Okay.
and
So that's
soldered.
a radiating element?
The whole thing is a radiating element, right?
Oh, and you're just shortening the size, you're lengthening or shortening the size of the oblong, basically.
Yeah, the frequency of this antenna is about just under 400 megahertz. As I said, I was aiming at 432 megahertz.
And when you move that up and down, that just changes this.
Just changes the
Low SWR,
SWR point for this area at its resonance point.
Yes.
The antenna itself, as I said, is just under 400 megs. I was aiming for 432 and I got it wrong. So I'm going to have to maybe cut off these and shift this piece down a bit to get it onto 70 centimetres.
Or just short, just very short.
Yeah?
Could you give us a quick sketch of the battery box that's giving us all that information?
It's a V&A.
It's a vector network analyzer. This is one of the fairly early ones, so it was fairly expensive. This was a $600 one.
Wow.
Pocket V&A, yeah.
And you need a computer to drive it.
Yes, that particular one, yes. No display on it, yeah. No. Yeah.
The slot antenna,
Yeah,
the size of the slot is the frequency.
yes.
The,
The
the
width,
size of the actual metal is not chopped away.
okay. Well, that's a good point. If you had an infinite slot of metal, right, you would have a main lobe out the front and a lobe out the side and a lobe out the other side that way. Okay? When you bring the piece of metal's width down till it's about half a wavelength, right, then you get a symmetrical pattern out the front and of course out the back. So roughly the optimum width of that is half a wavelength, right? So you could think of it as a dipole really, but a very flat one, right? So this aerial here is roughly half a wavelength from there down to there, and from there down to there. So it's actually roughly 0.7, 0.8 of a wavelength top to bottom. That's fairly deliberate, right? And that means that it forms a matching system, so the impedance in the middle is reasonably low to help with feeding it, right? So you can imagine from a thinking of where dipoles radiate, this is a dipole up here and a dipole down there, right? So it's going to have a bit of gain in the vertical, and of course, the slot being vertical, the polarisation is horizontal.
So what determines the width of the slot, Alan? The centre slot.
You can do what you like with the slot, it seemed to me.
Well, so what are the benefits and the downsides?
The benefits is to do with construction at frequency, right? For instance, mucking around with half wavelength loops of coax and stuff like that, and this antenna is more broadband than if you were doing dipoles and stuff. So for me as an amateur, if I can build a broadband antenna, it means I don't have to be accurate in its construction. And at the higher frequencies we get to, obviously the harder it is to do. So if I've got to muck around with getting my dipoles in a Yagi to an accuracy of like 1/4 of a millimetre, whereas at 6 metres I can have a whole centimetre of length in the end of the dipole elements. It makes it too hard. So you think about alternate antenna designs to make your own life easy in construction. That make sense? So that's often what I'm doing. Like that's why I built this kind of Vivaldi antenna, because I mean, how hard was that to make? Right. And similarly with this. Now our previous talker spoke about his biquad antenna. I've been using a biquad for satellite work for years now, and my backplane was the mesh from a screen door, you know, aluminium screen door mesh. Its mesh size is roughly at, 50 mil or thereabouts, which is a bit shorter, of course, than 1/10 of a wavelength for 70 centimetres. So that worked extremely well. So I've been using that for years. Just aim it up at about 15 degrees, which is optimum for satellite work. Yep. All right. The other antenna type I was going to talk about was the ZL Special. And I don't have much on the ZL Special except for my own web page work. Have I got it there or have I got it in? I think I had it in Opera actually.
Alan, I was going to point out the fact that as amateurs, we normally think of the metal parts radiating, but with slots, you've got to think it's the slot that radiates, not the metal parts.
Well, the edge.
It's both.
Okay.
Right. As I said, if you touch the metal here and here, you find that it varies the SWR a lot. So it's not just the slot that's radiating, it's the whole piece of metal. Because it's roughly a half a wavelength wide, right? Acting more or less like a dipole. It's just a very wide dipole. Okay. Right, you probably can't see a lot there in that picture, but that's looking up from the ground at my 6 metre ZL Special antenna. Let's go and have a look first of all at what a ZL Special actually looks like. Where is it?
No, we're just talking about your cactus.
All right, okay. So this is a basic idea of a ZL Special. That is where you have two elements, right? And connecting between them is a transmission line. Now the elements are spaced 1/8 of a wavelength apart. Yeah, this is all just my experimentation on the thing. And I looked at the 6 metre ZL Special because it shortens up your boom, because the distance between the driven element and the reflector, instead of being roughly a 1/4 wave, it now comes up to 1/8 of a wavelength, right? So if you're tight on space for building a beam, like you are on, say, 6 and 10 metres, and right, that is relatively attractive. And so I had a go at it, and if you scroll down the page, you'll see I've got some pictures from NEC. So I've got some pattern figures there, some pattern diagrams. Yep. Yeah, I can see you've got it on the screen there. Yes. Yeah. So that's not bad really.
2 elements, yeah.
Well, actually, that's for the whole 4-element beam.
Oh.
That's not remarkable, but
Space saving.
yeah, a bit of space saving. And so now one of the things I had to do with the NEC program, I actually had to talk to the developer of the software here and ask him, how do you swap the phase of the driven signal going to the second driven element? And he did give me how to do that, so that's in the files if you
So
ever
there
want
are
to download.
two driven elements?
There are two driven elements.
It's like two antennas in phase. Is that what you're saying?
Well, except that the phase is 135 degrees phase change,
Okay.
which is what gives you that one directional radiation pattern. But when you're building a beam, you soon find out that the first director actually sucks some power, as it were, out of the driven element, as in pushes it forwards. So when you're trying to counteract the signal from the back of the antenna, right, you need less signal going to that driven element than you do if it were just two elements. That makes sense? So, the next problem I had was, okay, so we've got an eighth of a wavelength between the two elements that are driven, but our coax cables have all got dielectric in them. So that means that the velocity factor is less. Right? So we can't, so if you have a look at the classic ZL special, they always use open wire lines between the driven element and the other one, so that the velocity factor is as close to 1 as they can sort of get to.
It's the same.
Yeah. So how do we manage all this? Well, under this NEC software here, you can start putting transmission lines between your various elements. So there's no reason why you can't feed your feed line cable somewhere in the middle between one element and the other, and have the signal going this way and the signal going that way. You can still achieve your 135 degree phase difference.
Use the alternate substitutes from the thin network.
So, no, it's not a collinear, it's a Yagi. So we've got two elements fed, being the basic two structure, right, and then you've got directors in front of that.
Yeah, when you're collinear, your elements are actually connected to driven elements.
Yes, but they're usually driven in phase. Whereas here we're doing a change of phase to get the other element to counteract the signal in the reverse direction. Right, to give us forward gain and nothing out the back. That's the whole purpose.
Collinear, usually the elements are in line.
Yeah.
Collinear, as the name suggests.
Yeah. Yeah.
And how much shorter do you get this bird compared to a 4-element Yagi? I mean, how much bang for buck do you get?
Well, that was my whole reason for doing this little discovery trip.
Right.
And in the end, I worked out it's not worth it.
Like there's a smidgen.
Yeah, that's right. It's not worth it. Right. Just build a
For the
4-element beam and be
complication.
done with it.
I remember years ago, Brian Connor had a ZL special on 2 metres that we used on a license there.
Yep.
It was quite compact.
Yep. And I actually, way back years ago, built a log periodic feed section to a 10-element 2-metre Yagi. Yeah.
How do you cope with a broad band? I mean, log periodic is a very broad band, and yet you
No, a log periodic doesn't have to be very broadband,
depends how many elements you got.
and how quickly you taper them down,
Right.
and their spacing. So you can build it for only a small bandwidth.
What's the benefit in that case? Just for fun?
Just for fun, really.
You can.
And at the time, Noise Brothers in Chatswood, Artarmon, had brass tubing at a good price, so I bought it.
Solution looking for a problem.
Yeah. Yeah. Okay, all right. Now, so where do we go from here? So any questions about my antenna systems?
Oh, after listening to all your presentation, the Sergeant Zorks would say, I know nothing. That's bloody compact.
Okay.
So,
All right.
with your coax, you join it in the middle to the two phases and stuff, so you're reversing one of the coaxes. So you couldn't just get away with it.
Eh?
Being
Well-
feed the coax through. I suppose you could
No,
use
no,
the
no,
end of the
no.
other end.
Even cleverer than that. You can get two pieces of 50 ohm coax, for instance, and put them in parallel, and then it becomes a 100 ohm line, right? If you connect them up one way, and if you connect them up the other way, you can halve it, so you can get 25 ohm line. And then if you go back to the picture of my actual antenna, can you go back to the picture of looking up at it into the sky? Yeah, it's on the same page. You can see cleverly that to get less feed to the reflector type element, the one at the far end of the boom, I've actually used a balanced line. And again, I found I had a roll of Teflon coated wire, and I twisted up a length of it and measured its velocity factor so that I could get the right length of it, and I empirically worked out its effective impedance. And so that's my piece of 100 ohm line going from my junction of all my coaxes and to each element. So that was playing around to see what was useful. Not really. But I would say though that if you've got limited space and you wanted a 15-metre antenna with some gain and some front to back, that the ZL Special is quite a good idea.
So as your frequency goes down, or the frequency of operation, the benefit of a shorter boom increases.
Exactly, yes. Yes. All right. Okay. Well, I think that's about enough from me, Alan.
Thank you.